Okay, I'm Jieming. This is a joint work with Nicole Immorlica, Aleksandrs, and Stephen Wu. So in incentivizing exploration, there are T agents coming sequentially in T rounds. Each of them can choose one action from a set of actions and gets a stochastic reward from the chosen action. We, as a principal, get their feedback on rewards and decide what information to send to future agents. Our goal here is to maximize the total rewards of all agents. So below is example, you can see there are 2 rounds, and we get feedback from 2 agents on 2 different actions. Now the third agent arrives. We need to decide what information to send to the third agent. We can just send all the information, and maybe the third agent will also buy the second cheapest option. All right. So in order to maximize the total rewards, we need to balance exploitation and exploration. Exploitation is to take the best action given the current information, and exploration is to try each action enough times to gather information. If we look at this example again, the first agent does not like the action of buying the cheapest option. However, it's totally possible that this action is the best for most agents. So if we only do exploitation, then maybe this maybe no agent will know this action is actually good, and most agents end up taking the suboptimal action. Okay. The challenge in this problem is that each agent only takes one action in one round. However, the benefits of exploration only accrued for future agents. Therefore, there are some misaligned incentives. And we need to think about how to incentivize exploration. Prior work studied this problem. You can find citations in my paper. One solution they use is to use information asymmetry. So if we consider a specific agent, when this agent arrives, the principal knows the history of all past agents. However, this agent only gets information from the principal. Prior work used this information asymmetry to recommend actions that might be suboptimal and guarantee that at the same time it's still incentive compatible for agents to follow the recommended actions. As an example, the principal can suggest the action with better history with probability 99%. In some situation, this is still incentive compatible for agents to follow, and there's a 1% chance for the agent to explore some other actions. All right. These results make no constraint on the format of information sent by the principal. And in theory, you can show that it suffices to consider policies which only use direct recommendations, meaning the messages sent by the principal are just recommended actions. Therefore, these results highly rely on the assumptions that agents are perfectly rational. These agents need to believe that the principal is running some incentive-compatible policy, and these agents follow the recommended actions even though they receive very little information. In our paper, we want to make more constraints on the principal's messages. We want the messages to be more informative. In particular, we require the messages to be subhistories, meaning actions and rewards from a subset of previous round. So here's an example of a history of 5 rounds. We can take 3 rounds from it, and we get a subhistory. Okay. Now, even with this constraint, from the agent's perspective, the principal can still do some complicated stuff. For example, if the principal really wants to recommend action 1, the principal can show agents rounds when action 1 has higher reward. Okay. So in addition, we make some more constraints. We want the subsets of rounds to be chosen beforehand. Therefore, all these rounds don't depend on the realized rewards. We further require our policy to be transitive, meaning if agent B sees the history of agent A and agent C sees the history of agent B, then agent C also sees the history of agent A. Okay. With all these additional constraints, we can guarantee that for each action, in a the rewards in a subhistory are unbiased samples from the reward distribution. Okay. With all these constraints, we consider a simple agent behavior model. Basically, this agent just look at the empirical mean rewards of actions in the subhistory and take the action with the highest empirical mean. Our results also work if the agent takes action with approximately highest empirical mean, but for this talk, let's just focus on the exact highest case. So we measure the performance of our policy by the regret, and it is defined as the difference between the total rewards of always choosing the best fixed action and the total rewards of our policy. We give a policy that obtains square root t regret. It is, we're hiding polylog t factors here, and this regret bound is optimal up to polylog t factors. Okay, and this result is for the case when there are only two actions, and this talk I'll focus the case when there are only two actions. Our result also extends to the case when there are more actions, but there will be exponential dependence on the number of actions in the regret bound. All right, now I'm going to describe our policy. I'll start by a simpler version. So this policy partitions agents into two levels. Level 1 agents come first. They are further partitioned into groups of constant size. And for each level 1 agent, it sees the history of all agents in the same group who come earlier. And we use a pass to denote that. The level 2 agent just sees the history of all level 1 agents. So this is a policy. And we show that if we use roughly T to 2/3 groups in the first level, we will get a regret bound roughly T to 2/3. Now I'm going to give a proof sketch of this regret bound. So we consider the gap between the mean rewards of the two actions. There are two cases. The first case is when the gap is small. This is easy. Basically, even if all the agents take the worst action, the total regret is at most delta times t, and it's at most T to 2/3. The other case is when the gap is big. We can show that if we set the group size to be a large enough constant, then in each group with constant probability, both actions are taken at least once. And then we can show with high probability, both actions are taken enough times in level 1. Because level 2 agent sees in all the history of all level 1 agents, they will see enough samples of both actions. And by a standard concentration argument, we can show that from the level 2 agent's perspective, the empirical mean rewards of actions are close to the actual mean rewards, and they will take the better action. All right, so this is a proof sketch. Intuitively, in this level 2 policy, first level agents focus on exploration, and the second level agent focus on exploitation. This regret is not the square root t, so how do we improve this regret bound? We just add another level. So we have, in this level 3 policy, we have log t copies of the previous 2-level policy structure, and we connect them to the third level. So how does this additional level help? Similarly as the two-level policy, the first level of this policy focuses on exploration, and the last level of this policy focuses on exploitation. The interesting part is the middle level. We want the agents there to do adaptive exploration, meaning we want these agents to explore more if the gap between the mean rewards is not too big, and we want them to do exploitation otherwise. Okay. And we can show that this policy gives some regret bound smaller than the previous regret bound. Okay. Let me give a proof sketch of this regret bound. So in the proof, we consider some good events. We show that they happen with very high probability, and condition on the events, the regret is small. The first event we consider is that level 1 groups explore both actions enough times. This is similar to the previous proof. The second event we consider is concentration. If an action appears in the subhistory n times, we want the empirical mean in this subhistory of this action to be at most log t over square root n away from its actual mean. The third one is interesting. We also want anti-concentration, and this is important for adaptive exploration. We can show that with high probability, constant fraction of level 2 groups sees some subhistory biased towards one of the action. Something like the empirical mean of the first action is slightly higher than its actual mean, and the empirical mean of the second action is slightly lower than its actual mean. Okay. So now we condition on these events. Again, we consider the cases depending on the gap. The first case is when the gap is really small, similar to the previous proof. Even if all agents take the worst action, the regret is still small. The second case is when the gap is big. In this case, we can show that the concentration of level 1 groups will guarantee that all level 2 agents take the better action. Similarly, the concentration in the first 2 levels also guarantee that all level 3 agents take the better action. Now we consider some case in between. So when the gap is small but not very small, we need to use the anti-concentration of level 1 groups to guarantee that both actions explore more times in level 2. And now with this more exploration, we can show that the concentrations in first 2 levels are enough to guarantee that all level 3 agents take the better action. Okay. There's a small range of gaps that's not taken by previous cases. It might be annoying. In this case, level 2 agents are not guaranteed to explore or exploit. You might so notice that this gap range guarantees that the exploration in level 1 is almost enough to guarantee that level 2 agents will take the better action. And also notice that level 2 agents only sees a subset of level 1 agents, and level 3 agents sees all the level 1 agents. Actually, the exploration in level 1 is enough to guarantee that level 3 agents to take the better action. So this is not a hard case. So this is the proof. Finally, we extend this policy into L levels, and here is a regret bound. If we take L to be bigger than log t, this regret bound will be square root t polylog t. Okay. I'm not going to the details. One thing worth mentioning is that if we simply generalize the tree structure of a previous policy, we won't get the good regret bound. We will get a log t to the L term in the regret bound. Instead, we use an interlacing structure. Basically, in each level, there are m squared groups, and m equals to some constant times log t. And for each level L group, it sees the history of level L-1 groups and all the level L-2 groups. You might notice that in the same level, several groups may share the history of lower level groups. But we show that it's fine. We don't really need a tree structure. This interlacing structure is enough to guarantee the concentration and anti-concentration we need in the group. To summarize, we studied incentivizing exploration with selective data disclosure, and we give a policy with roughly square root T regret. Here are the main ideas we use to construct this policy. For the two-level policy, we partition agents into groups to ensure exploration. For the three-level policy, we add a middle level to have adaptive exploration. And for the L-level policy, we interlace connections to reuse exploration. All right, thank you.